Hello, everyone. So guys, can you hear me?
Yes.
Okay. So just a small reminder on previous lecture.
On the previous lecture, we like quote unquote solved the problem of the scattering of a plane wave by the electric sphere, which is called Mie problem, where we introduced so-called Mie coefficients, which we introduced in the following way. We wrote that scattering field is a sum, is the following sum with coefficients A and B which are the scattering coefficient. This is called electric. This is called magnetic Mie coefficient. And we also spoke a little bit about general scattering problem. We spoke a little bit about the cross sections, the reciprocity theorem, and different ways to calculate the scattering, absorption, and extinction cross section. And just to remind you a little bit, basically we have three cross sections: scattering cross section, absorption cross section, and extinction cross section. And basically the physical meaning of these cross sections is, for this one, is like effective, like for three of them, the physical meaning is effective area. But for scattering cross section, it's obviously effective area that our like photons, electromagnetic field feels when it scatters on an object. For absorption is its effective area that absorbs objects, and for extinction it's like extinction is just absorption plus scattering. So this is like the effective area that interacts with photons, something like this. So you can think about, we can introduce some mechanical analogy. For example, we are like standing in the rain and we have an umbrella. We have an umbrella, very big umbrella. And let's assume that at the top of umbrella, we have some hole that absorbs particles of the rain. So we can think about the total area, like the total area of umbrella is, for example, we have umbrella with radius r, So the radius is r. Then the total area of umbrella will be like PR squared. Let me r big, and radius of this like hole will be r small. So the total area of umbrella will be PR squared. The radius, the area of the absorption, like part of the umbrella of this small hole, will be PR small squared, and this basically will be our extinction cross section, like quote unquote. This will be our absorption cross section, and therefore scattering cross section will be P r big squared minus r small squared. Something like this. It's just like hand waving analogy. It's just a hand waving analogy. Okay. Okay, so basically, there are like if we will look at the scattering coefficients, if you will look at scattering coefficients as a function of the wavelength, we will see actually something like this. For example, let me plot it. Let me plot it something like this. Just 1 second. Okay. So this is basically the scattering cross section for a dielectric sphere with radius equal to 100 nanometers and epsilon equal to 4, or n equal to 4. And we can see here that we have like, in some sense, we have here 3 regions. So the first region is somewhere here, like the first region. And basically, here we have no resonances. Here we have no resonances. The second region is approximately somewhere here. We have here first like some, here we have some first resonances, but they are pretty much like far apart from each other. So we have here like few resonances. And in this region, in the third region, we can see that there are so many resonances that we basically are unable to distinguish between them. I don't know, let me say a lot of resonances. And actually, it's not very clear from here, but I will try to maybe increase this part of the region. and show it to you. Yeah. This is the part from 0 to 200 nanometers. And basically you can see here that the value of the scattering cross section, it goes to some like in the limit omega goes to infinity, it goes to some particular value, which in this case it's 1.4, I think. It's 1.4. And we can actually calculate this value. But I will tell you a little bit later about this. So we see that the most important thing right now is that we have here 3 regions. And these 3 regions are distinguished by the geometrical parameters of the scatterer. So just to remind you, the radius is 100. Sorry. The radius is 100 nanometers. The refractive index is 4. So, like here, so we will distinguish these regions by the size parameter that I introduced on the previous lecture. It's A N K0 without N, it's just AK0. In this region, it's 100 nanometers multiplied by, I don't know, 2 pi over 1000 nanometers. And it's approximately 0.1 multiplied by 2 pi. In this region, for example, let me take 500 nanometers for simplicity. It will be 100 nanometers divided by 500 nanometers multiplied by 2 pi. It's approximately, will be approximately pi over 2.5, so it's approximately like 1. And in this region, obviously, the size parameter will be much bigger than 1. So here, size parameter is is less than 1. Here it's approximately 1, and here it's much bigger than 1. And in this case, actually, what is happening and why we have some limiting value here, our sphere is like very, 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 very large. I don't know, you would have to draw it. So the radius of the sphere is so big that the plane wave feels it almost like, for the plane wave, this sphere is almost flat. It's almost like the boundary between just a boundary between 2 media. So just a refraction on the boundary. And I think we can even calculate this. So in the end, actually, this limit is basically like the value of the reflection coefficient. it will be just the value of the, well, not normalized by some number, but it will be just the value of the reflection coefficient. So when lambda here goes to 0, our sphere for our plane wave is so big that it is just like just a boundary between two media. In this intermediate region, we have just some resonant structure. We have here our first resonances of the structure, so it is just, we have here some resonance, and this is like intermediate region. But in the region where there are no resonances, we see that there are just some like power dependency on the wavelength, and here it's actually lambda to the power -4, and I will show this to you a little bit later. And these three regions are called, this region is called geometrical region, because in this region we can approximate our sphere by just a very big I don't know how to say this, very big just flat interface. And in this region we can explain like everything by the geometrical theory of light. This region is called Mie region because it in this region is described. In this region they will calculate like scattering, absorption, and everything like this using the Mie theory. And the third region is called Rayleigh region, because Rayleigh was like was studying it a lot, and in the geometrical region our structure is much bigger than X, which basically it means that the size of our structure is much bigger than wavelength. Maybe let me write it here. So geometrical region, Mie region, and Rayleigh region. In the geometrical region, the size parameter is much bigger than 1, which basically means that the size of our structure, in this case it's radius, but this theory is applicable not only to spheres, but in some sense to any scatterer, to cylinders, to, I don't know, to some arbitrary scatterer. And we have some like size parameter. For example, in cylinder, it can also be the radius of the cylinder or the height of the cylinder, just some effective size parameter. In the Mie region, the size parameter is approximately 1, so the radius of the size of our structure is approximately equal to wavelength. And in the Rayleigh region, the size parameter X is much less than 1, which means that our structure is much less than the wavelength. Yeah. So this region can be described by geometrical optics. And in this region, particle is very small. And basically what we are doing here, we consider our particle just as a point dipole. So we have the plane wave and point dipole. We consider particle just as a point dipole. So the physical meaning is following. But there is also one important thing is that actually the meat theory is a rigorous theory in the sense that when we were deriving the Mie coefficients, we didn't make any assumptions about the size of our sphere. We just said that there is some size, and this is why Mie theory actually can describe all three regions. This is a very important thing to remember, that Mie theory is a general theory. It's like general theory of scattering. For the case of the sphere, for example, we derived it for the case of the sphere, but we can derive it for like any arbitrary scatterer, either numerically or analytically. And Mie theory, because it is a rigorous theory, it can describe all three regions. But because we can't make any approximations in this in this intermediate region, we call this like Mie region, something like this. And actually,
Question.
Yeah.
Strange, maybe why we consider particle in Rayleigh region as a dipole, not a monopole or another?
Well, because we have no scattering from the monopoles, because monopole do not radiate. You see
And next to the quadrupole or something like this, and others.
The dipole is the first order. So basically, how to say this? Well, of course, like we have here in the sketching. Here in the sketching, we have all orders. Maybe let me maybe let me derive this to you somehow. Just give me a second. So, well, I think that in a more or less hand-waving fashion, I can I can write it like this. So we have, for example, let's consider some of the Mie coefficients. For example, for simplicity, we will take an electric Mie coefficient. BL equals to JL of nx multiplied by x, JL of x minus JL of x and xJL of n x prime divided by x hash L of x prime minus HL of x and xj of nx prime. So something like this. Basically, in this region, in Rayleigh region, we work in the limit of a very small x. So the x is much less than 1. And in this limit of very small x, basically we can write that this is not very rigorous. It's not very rigorous. But we can write something like this to L plus 1 factorial x to the power L. And here, and for the Neumann function, this is equals to minus 2L divided by 2L to the L factorial 1 divided by XL plus 1. And basically the Hankel function is just Bessel function plus I, well, the first order, the one we use here, plus I Neumann function. So let's consider, for example, the first two. Let's consider L equal to 1. We can just, I will not like take the rigorous limit, but we can hand-wavingly say that, basically this is like B1 of x in the limit x to 0
Excuse
will...
me.
Yeah.
I'm sorry, but could you please explain why we do this? We want to express why is it a dipole in Rayleigh? Yes?
I'm trying to explain why we consider only the dipole in
Yes.
Rayleigh
I'm
sketching.
about this. Yes, okay. So I'm
Yeah. So basically, what I will do right now, I will try to like hand-wavingly do like in some sense Taylor expansion of this of the dipolar and quadrupolar Minkowski coefficient, and you will see that quadrupolar Minkowski coefficient is much less than dipolar, something like this. So this will be like, basically I will just change this like to this. This will be x, the derivative will be proportional to like it's xjl minus plus jl prime, which is just a sum of jl minus 1 plus jl plus 1. So this will be x to the power 0, this will be x to the power 2. So this guy is just basically x squared. So this is just multiplied by x squared minus once again x, and this guy is just nx squared and divided by nx multiplied by this will be x minus I over x minus No. This will be like. This will be once again. It will be x h derivative plus plus h. Oh no, I messed everything. Well, okay, maybe actually I can show you. I think it will take a lot of time, but basically, okay, no, let me finish this. I made a mistake here. Sorry, guys. So this first guy will be just. This first guy will be just x. The second guy will be x j prime plus j. So the derivative of a Bessel function is, if I remember correctly, jl plus 1 plus jl minus 1. Let me check this. Let me check this. Let me check this. Boom. Well, while I'm trying to find it, let's just assume that this is. Let's assume that this is correct. So this guy will be something like x multiplied by okay, spherical Bessel J and x okay, yeah, it seems that this is just a minus here. So this guy will be like x multiplied by x. No, the minus here, like multiplied by x0 minus x squared and plus x. So this is like approximately, we can approximately write this as x to the power like 2x minus x to the third power minus, well, okay, it takes a lot of time. Sorry, maybe let me just plot this to you. So I don't know, from 1000 to 1400 nanometers. So for example, if I will plot the Scattering cross section to you, well, basically what I was trying to show, I was trying to show that in the limit x equals to 0, b2 of x divided by b1 of x goes to 0, because b2 of x will be much smaller than b1 of x. So basically, when we consider this Rayleigh scattering, like all the quadrupole, octupole, and like all other modes, they basically do not make any contribution to scattering compared to the dipole. So the dipole is like the first order in the expansion. The quadrupole is the second order, and well, something like this. So basically here I plot the scattering cross section. This orange is dipole, the green is the quadrupole, the red is octupole, and the pink is hexa, deca, pole, if I remember correctly. Basically, this is L equal to 4, this is L equal to 3, this is L equal to 2, and this is L equal to 1. So, and what I want you to see here is that this y-axis is logarithmic. So we see that and the blue is just a total cross section. So we see that, for example, the dipole here, the dipole scattering, well, for example, here, it's just 10 to the minus 2, something like this. And the quadrupole scattering is it's 10 to the power minus 6 already, because it's micra. And the octupole is like 100 to the power minus 12, and this is basically 10 to the power minus 16, something like this. So basically, when we look at scattering field, we can just leave only, for example, as a function of x, we can leave only in the limit x equals to 0. This is basically just a sum of a1 of x by m plus b1 of x by well, it was yeah. Something like this. So this is like a Taylor expansion. We leave only the leading order in this expansion, and this leading order is dipolar. This is just a dipole. We, of course, like rigorously, we can consider quadrupole and all of this, but the contribution to a scattering absorption of the quadrupolar mode will be much less than of the dipolar mode. And we just, of course we can, but we want to make everything simple. And this is why we consider only the leading order mode, only the leading contribution, which is, as you can see from here, which is like much larger than the next order. So something like this. Was it clear, or it was a little bit of mess in the beginning? So basically, you can try, maybe you can try at home. You can take this coefficient and make an expansion of this, just a Taylor expansion for the x parameter, and basically you will see that the first leading order for B1 coefficient is much larger than the first leading order for B2 coefficient, something like this. Okay. Do you have any questions about this, or is it clear?
Okay. Thank you.
Okay. Okay, so let us take a little bit closer look to this relay regime. So let's speak a little bit about this relay regime. As I told you before, the particle is so small. The particle is so small that we can consider this particle just as a dipole. Something like this, with some dipole moment d. And we have a plane wave. We have a plane wave. Once again, we have here like k vector. We have some electric field going like this. The incident field is oh well, just some E0 of R and C. This is just some IK Z minus I omega T, something like this. And well, we can even write it like this. No, I will still write it like this for generality. So we know that the dipole moment of this particle, will be equal to the dipole moment of this particle will be equal to the polarizability of the particle multiplied by E0 multiplied by exponent minus I omega T. For example, let me the coordinates of this particle. The particle is in the origin of coordinates, so like 0, 0, 0. And once again, this is like z-axis, this is x-axis, something like this. And we can actually calculate the extinction and scattering cross sections for an absorption cross section for such particle. So if you remember, we had the following equation that extinction cross section, we can calculate the extinction cross section as 1/2 real part of the integral of the current that is made of currents inside our particle multiplied by E0 of R over dV. This is over dV particle, something like this. And for a point particle, we know that currents are connected. The current of R is basically of R and T is basically the time derivative over the polarizability, but in our case, because everything is time harmonic, this will basically be just minus I omega P over R and T. And also for the dipole, the polarizability is just delta function of R minus R0 multiplied by the dipole moment. This is position of the dipole. So we can rewrite this expression. We can rewrite this expression in the following way. This will be 1/2 real part of minus I omega integral. Integral of minus I omega delta function of R, because
that
here,
in
yeah.
first line P is the power, and in the second
Yeah. So, sorry, this is like extinction power, and this is polarizability. Yeah. This is also polarizability. So yeah, this will be like this current will be minus I omega multiplied by delta function of R, because R0 for us is 0. And multiplied by the dipole moment of our dipole. Everything is conjugated and multiplied by incident field of R and T, integrated over the whole volume. Because we have a delta function here, this will be just 1/2 real part of minus I omega delta dipole moment of T. Well, after the conjugation, minus I because becomes I, and here we have dipole moment conjugated multiplied by just, if we substitute, if we take and substitute this here, we will have just E0 multiplied by exponent minus I omega T, something like this. And we also substitute this expression here. We substitute this expression here. Yes, and in the end we have 1/2 real part I omega alpha conjugated, E0 conjugated, exponent I omega T multiplied by E0 exponent minus I omega T. So this is basically omega over 2 E0 squared, and real part of I alpha conjugated will be just imaginary part of alpha. Something like this. And this is our extinction power for a small particle. So for the extinction cross section is extinction power divided by square by the modulus, not square, just modulus of the Poisson vector. For a plane wave, it will be just c over 8 pi E0 squared. So the extinction cross section for a small particle will be c over 8 pi over c omega over 2 E0 squared divided by E0 squared, imaginary part of alpha. So we can cancel out these guys. Here it will be like 4, and omega over c will just give us the wave vector. So for a small particle, extinction cross-section can be calculated as 4 pi k0 imaginary part of the polarizability. This is when radius of the particle is much less than the wavelength. So we can see that basically one important thing is that the extinction cross-section is proportional to the imaginary part of polarizability. So if imaginary part of polarizability of the particle is equal to 0, it means that extinction cross-section is equal to 0. So this particle, in the sense, it do not interact with the incident field. This particle do not interact with the incident field in any way. Basically, incident field don't feel this particle at all. But there are some nuances about the polarizability, which I will show you a little bit later. And also, let me also calculate. Let me also calculate the scattering cross-section for a small particle. The scattering cross-section for a small particle. So we can calculate the scattering cross-section from using the same equation, actually. J multiplied by E scattered. But in this case, we need to calculate this E scattered, which is, it will be not very convenient, but it is very good that we have another equation, that we have that for the scattered cross-section, we can just take the scattered power. We can calculate actually, because it is a dipole, because our particle is a dipole, we can actually calculate this scattered power in a very easy way, because we know the expression. We know the expression for the power. How to say this? Radiated power of a dipole. The radiated power of a dipole is just 1/3 omega 4 divided by c to the 3rd power square modulus of the dipole. Okay, how to say this? Of the dipole moment. Yes. This is just in case you don't remember, this is just a well-known formula for the power of a dipole, for the radiated power of a dipole. And because we have a dipole, because our scattering field is basically what this dipole is radiating, we can use this expression. So the scattering cross-section, in this case, the scattering cross-section will be just 1/3 omega to the 4th power divided by c to the 3rd power, the dipole moment squared, and divided by the Poynting vector, which is c over 8 pi E0 squared here the dipole moment is alpha E0 exponent minus I omega t. So this becomes 1/3 omega 4 c to the third power alpha squared E0 squared divided by c over 8 pi E0 squared. Once again, we cancel out these guys. And in the end, we have 8 pi over 3 k0 to the fourth power modulus square of the polarizability. Modulus square of the polarizability. So for the small particle, the sketching cross-section for the small particle will be 8 pi over third k0 to the fourth power square modulus of the polarizability. This is for the when the wavelength is much bigger than the size of the particle. And we see that this guy is proportional to the 1 over lambda to the fourth power. To the 1 over lambda over fourth power. And this is actually what we saw, what we see here in this, like in this region. Basically, this curve, if you will plot it, this curve is proportional to the 1 divided by lambda to the fourth power. And we can actually calculate this from the, like approximation of the sketching theory, something like this. And this is actually the reason. This is the reason why we have blue sky during the day and why we have red sunset. So we know that like, well, the sun has the maximum of intensity in the green part of the spectra, but the sunlight, what is happening, well, here we have our Earth. Here we have some atmosphere, and for example during the day the sun is somewhere here and it is like shining some light, and the atmosphere is just basically a collection of dipole particles, because molecules of ozone and oxygen and nitrogen and all of these gases, they are, for them, the size of these molecules is much less than the wavelength, well, in the visible range. So what is happening is that the field, like when we look directly at the sun, for example, how to draw this, I don't know. For example, we are standing here. And we look directly at the sun. Of course, we will see sun as a big white thing, because it emits so hard that we see it as just a white thing. But if we will look somewhere here, for example, if we will look I don't know, in this direction, for example, like in this direction, we will see just the sky. We will see just the sky, and the sky will be blue. This happens because the sketching cross-section is proportional to 1 divided by lambda to the 4th power, and it means that the red light for the red light sketching cross-section each is much smaller than for the blue light. So this is why we don't see any red color here. We see only the blue color, because all the red color, all the red light goes like this, but all the blue light, it goes here, and then it scatters, and we see the sky just as the blue. Well, of course, like the sketching cross section for the UV is also it's bigger than for the blue, but human eye is an integral. In how to say this? Human eye basically integrates the spectrum, and after the integration, the peak is not in the like violet. The maximal peak is like this blue color of the sky. But what is happening at the sunset? At the sunset, sun is. Let me draw it more accurately. At the sunset, here are we, and the sun is somewhere here. At the sunset, the light goes like through this part of the atmosphere. During the midday, it goes through this part of the atmosphere. Let me write like L1 and L2. And obviously, L1 is much bigger than L2. So this is at sunset. And because of this, actually, the blue light is like all blue light is scattered, and the intensity of the blue light becomes so negligible than the intensity of the red light. So we don't see any blue light on the sunset, because like the distance that the light propagates at the sunset is much larger than the distance at the during the day. All the blue light is scattered because its scattering cross section is much larger than for the red light, and we see this like first orange and then red sunset, something like this. Do you have any questions about this or not? Okay, and last thing before the break. So we derived that extinction cross section equals to the 4 pi k0 imaginary part of the polarizability, and the sketching cross section equals to 8 pi over 3 k0 at the 4th power square modulus of the polarizability. So we know that if we have no, not like this. We know that sigma extinction cross section is a sum of scattering cross section and absorption cross section. And because of this, if we have no absorption, this means that extinction cross section equals to scattering cross section. So basically it means that 4 pi k0 imaginary part of polarizability equals to 8 pi divided by 3 k0 to the 4th power square modulus of the polarizability. Because we have no absorption in our particle, we can assume that imaginary part of polarizability is much less than real part of polarizability. So let me maybe notate this as alpha 2 prime and this as alpha prime for the simplicity. And because the particle is very small, we can say that real part of polarizability equals to the real part of polarizability equals to the alpha 0, which is like static polarizability. Well, basically, this is polarizability in the limit lambda goes to 0. So we can put these assumptions into this equation, and we will get 4 pi k0 alpha 2 prime equals to the 8 pi over 3 k0 to the 4th power multiplied by alpha 0 squared plus alpha 2 prime squared. Something like this. And we can put everything, because here alpha 0 is much larger than alpha 2 prime from this assumption, because we have non-absorbing particle, so we assume that like imaginary part of polarizability is very small. We can we have the following expression: 4 pi k0 alpha 2 prime equals to the 8 pi divided by 3 k0 to the 4th power alpha 0 squared. So imaginary part of polarizability equals to 2 divided by 3 k0 to the 3rd power alpha 0 squared. So the polarizability in the end we have the following, that polarizability of the particle is alpha 0 plus 2 over 3rd I k0 to the 3rd power alpha 0 squared. Well, it's positive, so it's a real number. I mean, it's real number, so something like this. So what we actually can, and one important thing that we can see from here is that for the small particle, imaginary part of polarizability is always non-zero, even if we have no absorption. So this looks kind of strange because imaginary part is always associated with some losses. For example, imaginary part of permittivity tells us about ohmic, like material losses in our system. But here, even if we have no absorption in our particle, we still have some imaginary part of polarizability, because if the imaginary part of polarizability is zero, this will give us zero extinction. So the particle should have some imaginary part in order to scatter the light, even if you have no polarizability. Something like this. So do you have any questions about this part? Okay, if no questions, then I suggest to make like 15-minute break. See you in 15 minutes. Guys, can you hear me?
Yes.
Okay. So I noticed that I made a small mistake in the last part. So basically, we are doing the following thing. Yeah, we're saying that the imaginary part of alpha is much less than modulus of alpha, and we're saying that real part of alpha is approximately like static polarizability. So we arrive from this equality, we get that imaginary part of polarizability equals to 2/3 k0 to the third power alpha squared, which means that alpha equals to real part of alpha plus 2/3 k0 to the third power alpha squared. We put this to the left part, and it's like alpha 1 minus I 2/3 k0 to the third power alpha equals to alpha prime. And basically here, because it's like modulus of alpha. No, because of this property, we write alpha approximately as alpha 0 here. So, and in the end, we arrive at something like, and we also write alpha 0 here.
Excuse me, could you please scroll high for a second? Yes, a little bit more. Okay, yes. Thank you.
This is basically, in the end, we have something like this, that polarizability of a small particle is alpha 0 divided by 1 minus I to third of the k0 to the third power alpha 0, where alpha 0 is static. It's a static polarizability. So, and basically, we can actually get this expression from the Mie theory. From the Mie theory, we can, if you remember, the Mie coefficients are basically proportionality coefficients. They like coefficients before electric and magnetic harmonics, before like dipole, quadrupole, and all of these like harmonics. So on one side, we can expand electric field, scattered electric field. We can expand it in like in the multiples. So this is like polarizability multiplied by dipole moment plus quadrupole polarizability multiplied by the quadrupole, like dipole polarizability multiplied by dipole moment, plus some like quadrupole polarizability multiplied by quadrupole moment, and so on and so forth. And on the other hand, we can express in terms of this vector spherical harmonics and Mie coefficients, like A1 and electric 1, 0 plus A2 and electric 2, 0, and so on and so forth. And basically, this A1 is just this is just like dipolar mode. This like N2 is quadrupolar mode. And if we do these two like expansions, we can actually see that we can express dipole polarizability. We can express dipole polarizability in terms of Mie coefficients, that dipole polarizability actually actually equals to 3I over 2K A1. And if we will expand A1 over X as in a series of X here, just a reminder, is A K0. If we will expand this expression, we will get something like this, minus I 2/3 yeah. Yeah, it's correct. It's not it's epsilon minus 1 divided epsilon plus 2
Can you-
multiplied.
Sorry, can
Yeah.
you repeat, please, how we obtain the equation for alpha?
This one.
Yes.
Well, basically we can expand our field. For example, like on electrostatics, you expand your field into a series, like the dipole moment, quadrupole moment, octupole moment, and like all of these other moments, higher order moments. So here it's also like electric field of a dipole, electric field of quadrupole, and so on and so forth. But on the other hand, our scattered field is a series of vector spherical harmonics, and each like order is proportional to some multiple. This is why we call them like dipole, quadrupole harmonic, octupole harmonic, and so on and so forth. And but like in some sense, they are a little bit different expansions, but we can express the electric field of a dipole using this dipole vector harmonic. We can express the electric field of a quadrupole using this quadrupolar vector spherical harmonic. And basically what you have, you have a function, which is our electric field, and you have two different expansions. A1, I don't know, let's call it V1 of X plus like A2, V2 of X plus, and so on and so forth. And you have another expansion like B1 U1 of X plus B2 U2 of X plus, and so on and so forth. And you notice that V1 is actually of X is equal to C1 of X, C1 multiplied, just the coefficient by multiplied by U1 of X. So you just compare these two expansions, and you can get that A1 is A1 multiplied by C1 is equal to B1, something like this. And here in this expansion with multiples, we have this different coefficients like dipolar polarizability, quadrupolar polarizability. We have this polarizabilities. In the expansion with vector spherical harmonics, we have these Mie coefficients. But in the end, we can express, for example, electric field using this electric dipolar vector spherical harmonic. We can express electric field of a dipole using this vector spherical harmonic, and we can express electric field of the quadrupole using this vector spherical harmonic. So in the end, if you will compare these two different expansions, we will see that electric polarizability is proportional to the first electric me coefficient, something like this. Basically, well, how to say
Sorry?
this? Yeah,
What alpha?
alpha is
We have
is
different alphas.
It's-
Dipole, quadrupole, and others.
it's electric polarizability.
Yes, but in our
Yeah, of a dipole.
sorry. Mhm.
Of the polarizability of.
So the question was about this coefficient. Okay, I understand that we see on two series and write this, but I can't clearly understand why the coefficient is like this, proportional to k in order -3.
This is just like, well, how to say this? Well, if you will derive everything rigorously, you'll get this expression. I don't want to write this series and then write this series and then compare this and derive because it will take a lot of time. So how to say this?
Okay, can you first remind what is the dipole and quadrupole electric field, how it looks like?
Basically, the electric field of a dipole, is can be calculated as a green function r minus r0 multiplied by the dipole moment So basically, we can express this green function. In terms of vector spherical harmonics. How to say this? This is basically a dyadic green function, and this is the dipole moment. So the dipole moment, we can express the dipole moment as alpha E0, something like this. So in the end, electric field of a dipole equals to the polarizability multiplied by the green function of r minus r0 multiplied by the electric field E0. The green function has a big expression, like very, very long expression, but maybe I can try to explain this to you very quickly. You want like to get the rigorous expression for the electric field of a dipole in terms of vector spherical harmonics, yes?
Yes.
Maybe I can do it in a following way. Let me just open one book. It was.
Or you can tell us what a book and we can see it by
No,
ourselves.
I need to open one book and make a couple of mathematical stuff, I think. Vector wave equation. Where is the green function? Yeah, 387. So because I was thinking about telling this to you a little bit later, but maybe I can do it right now. Well, we know that these vector spherical harmonics, they form an orthogonal, like orthonormal, not orthonormal, but like complete orthogonal basis. So we can express basically any vectorial function using vector harmonics, like cylindrical vector harmonics, spherical vector harmonics, like any that we want. And in this sense, we can actually express even the dyadic green function in terms of this vector spherical harmonics. So the expression will be like this. I will just show it to you, and then I will explain it to you. So we have a dyadic green function, which is a solution of the following expression minus k0 squared of the following equation, r minus r0, k0 equals to unit tensor and delta function. Just to be sure, do you are you familiar with this dyadic green function and all of this stuff? Are you familiar with this equation, or do I need to explain it?
It's not
Guys?
familiar for me.
Okay, so do you know what the green function is in general? When we use the green function, what is this and all this?
I am quite null.
Sorry?
Quite
Can you
null.
please repeat? What do you mean by quite? Are you familiar or not? Or
No.
like a little bit. Okay. Let me think how can I explain it in a fast way. So I will try to explain it very briefly. But if you will have some questions, I will just maybe I don't know, try to explain it on the next lecture or something like this. So for example, we have some differential equation. I don't know, this can be like the Helmholtz equation, for example, one-dimensional Helmholtz equation. But right now I will we can write this like Helmholtz equation in the following way. So this is some differential operator, let me call it L. But in a general case, this theory is applicable like to any differential equations. So yeah, for example, let me consider some differential equation which you write in the following form. Where this is like some differential operator. For example, this is homogeneous equation, and this will be, this guy will be like non-homogeneous equation. Non-homogeneous because we have some source here. Yeah, we have some source here. The question is how to solve this non-homogeneous equation. In the general case, if you have some like very complicated source, like some very complicated function, I don't know. For example, we have like we have this Helmholtz equation plus k squared u of x and I don't know, some product of Bessel function, some sinus of 2 pi x divided by x to the power 1000, and I don't know, some Legendre polynomial 2, 1 of x hyperbolic cosine of x, it will be almost impossible to solve this equation for us. But we can notice one thing. There is one very important property of the delta function, which is like maybe its main property of the delta function, that if we have an integral, if we have the following integral, delta of x minus x0 over dx, this guy equals to f of x0. So, for example, in our equation, in our non-homogeneous equation, let me write f of x as this integral from minus infinity to plus infinity, f of x prime, delta function of x minus x prime over dx prime. And let me also make the following assumption. Let me assume that our function u of x can be expressed in the following way. Can be expressed as some function g of x and x prime multiplied by f of x prime over dx prime. This is like we make like quote unquote, we make the following assumption. Well, I will not like speak about like rigorous mathematical stuff here, but for the moment, like hand-wavingly, let's think that we can do like for every f and for every u, we can find the following function. If we will put this guy and this guy here, we will get the following equation. So it's L integral from minus infinity plus infinity g of x and x prime f of x prime over dx equals to integral from minus infinity to plus infinity f of x prime d of x minus x prime over dx prime. We recall that this is differential operator that acts on the x coordinate, not on x prime coordinate. So this guy for this differential operator is just a constant. And we can like, because everything is quote unquote good from the mathematical point of view, because this integration is over x prime, this acts on x, we can actually exchange this like integration and differentiation. So in the end, we will have something like this. This will be like integral of f of x prime, the L acting on this g of x and x prime, and from the left side we have here minus delta function of x minus x prime over dx prime. So we can see that this equation, this like very hard equation, is reduced to the following equation: g of x and x prime equals to the delta of x minus x prime. So if we know this function g, we can basically solve this equation for any f of x, like any functions that we want. And the solution will be just the convolution of this g function with function. This is like solution of this differential equation with any right-hand part. So, and this function is actually called the green function. For example, you can read about this on Wikipedia. Also, you can read about this. I was teaching myself what is green function from the book of books called Classical Electrodynamics, and the author is Jackson. Also, you can read the book by Principles of Nano-Optics. By Novotny. And like more, I think more mathematical approach is, if I remember correctly, it's something like methods of mathematical physics by Morse and Feshbach, something like this. I don't remember. I don't really remember the names, but I think you will be able to find this in the internet. So basically, green function is a function that allows us to the green function is a function that allows us to find the solution of non-homogeneous differential equation for every right-hand part. So, for example, in the case of scalar Helmholtz equation, the green function will satisfy the following equation: g of x and x prime equals to delta function of x minus x prime. We can also write the green function for the three-dimensional case. In the three-dimensional case, it will be something like this: g of r and r prime plus k square g of r and r prime equals to the three-dimensional delta function, which is just delta of x minus x prime, delta of y minus y prime, delta of z minus z prime. What else? And do you understand this part? It was a little bit of a mess because I was not ready for this, but I think is it like clear what is green function? Why do we need green function? Why it is useful? Or do I need to make some more comments?
So I think yes, it's getting more clear.
Okay. So then about this dyadic green function. We are working with electromagnetic fields. We work with electromagnetic fields, and this electromagnetic field is a vector. So from the Maxwell equations, from the Maxwell equations, we can derive the following. Like maybe let me do this like quickly. Electric field plus equals to IKB, and the second equation is magnetic field equals to minus IK E plus for P over C J. So basically we take the curl of this equation and we get that this is just air. So epsilon equal to 1, mu equal to 1. Just for simplicity. We can do it in the other case, but just for simplicity, let's do it like this. So we will have something like curl of the curl of electric field equals to IK curl of magnetic field, which is just the curl of magnetic field is just minus IK E plus 4P over C J, which is just some current. In this case, it's the source in our equations. So in the end, we have the following equation for the electric field, curl of the curl of E. We put this to the left side, minus k squared E equals to IK for pi over C J. This is like also like when we have divergence of E equals to 0, we can write that curl of the curl of E equals to the minus Laplacian E and get the usual form of Helmholtz equation. But right now I will stop just on this form because in this case we made no assumptions about if we have like tangential or solenoidal or not solenoidal electric field, something like this. Because for example, if we have some charges here, then we will not get like this form. So this equation, this form of wave equation is more general one. So we see here that we can actually apply the same formalism as with the scalar equation. We can apply it here, but we see that electric field is vector. The current is also a vector. So we need to have, if we have like the green function in this case, we need to have like something like this. Electric field of R should be equal to integral over all three-dimensional space, like V infinity. Let me call it like this. It should be something here of R and R prime multiplied by the current of R prime D 3R prime, something like this, and integrated like from minus infinity to plus infinity. And this guy is a vector. This guy is also a vector. Of course, two vectors can be connected using the scalar. But also we can get a vector if we multiply another vector by a matrix. So in this case, like when we have a vectorial differential equation with vectors, with the source as a vector and with our function as a vector, the green function is actually, in the general case, it's a matrix. And this is why it's called dyadic green function, because it's actually not any random matrix, it's a dyad. Dyad is basically there is such thing as, well, we have an inner vector product which is like just U1 C1 plus U2 C2 plus and so on and so forth. But we also have such thing as outer vector product. And it's a matrix with elements O1, C1, O1, C2, and so on and so forth, and like O2, C1, and O2, C2, and like this. So basically, the outer vector product will be a matrix with elements OI, CI, or OI, CJ, something like this. So this is like dyadic green function. Yeah, and this guy is actually called dyad, if I remember correctly in English. And we can even derive like this dyadic green function in the well, I will not derive it, but you can see about the derivation, like in some general way. You can read about this dyadic green function. It's let me find the pages. For example, a very good book is this Principles of Nano-Optics by Novotny, and you can read about green function in two places. The first one is the paragraph 2.10. It's about dyadic green function. I just want to make a comment that here he writes everything in SI system of units, and I write here everything in CGS. So the notation may be a little bit different, but basically you can find here about the mathematical formalism, some like basic math of the green function. You can find it here. You can find also about green function for scalar equation, and you can find about dyadic green function, about connection of dyadic green function with green function of with like scalar green function, because you can express one from another. Well, in the nutshell, do you know what vector potential is? What vector and scalar potentials are?
Yes, we know what is it.
Sorry, can you please repeat?
Yes, we know. It's familiar to us.
Okay, so basically, like from Maxwell equations, you can, well, just in the case if somebody doesn't know, you can introduce two potentials. You can introduce vector potential like this, and you can also introduce scalar potential. But in the nutshell, from Maxwell equations, you can derive Helmholtz equation for this vector potential, which will look something like this: some proportionality coefficients, and don't remember, multiplied by current of R. And you can calculate this vector potential as using just the green function for the scalar Helmholtz equation. but the electric field no, it will take a lot of time. Okay, sorry, you can just read about this in the book. And the another paragraph is paragraph 8.3. It will actually give you the electric field of a dipole and like the green function for a dipole and so on and so forth. But returning back to the original question, we can express, so we have this like dyadic green function, which is the solution of the following. It is the solution of the following equation. Something like this. And because because the dipole is basically for the dipole, we have something like this. It's like dipole moment multiplied by the delta function. This is basically the current of an electromagnetic dipole. The electric field of the dipole can be the electric field of the dipole can be written in the following way: the dipole multiplied by the dipole moment. And yeah, and we write the dipole moment as follows: E0. But on the other hand, because we remember that we have complete orthogonal set of vector spherical harmonics, there is actually an expression for the green function, like for this green function, which is of this Helmholtz equation in terms of vector spherical harmonics. And this expression is following. This is from waves and fields in homogeneous media by Chu. So basically here, like in my notation, this is like L. So each n here is L, but I will leave it like this here. So this is expression for the green function which satisfies the following equation. You can find the derivation in this book. It's like k0 squared green function of R and R prime. K0 equals to d of R minus R prime. Basically, you can derive it in a very simple way. You just say that the green function is a series over L from 0 to infinity, M from minus L to L. But because it's not a vector, because it's like tensor matrix, quote unquote matrix, the coefficients will not be scalars. they also will be like matrix A, ML, the coefficients like will be not matrix. Sorry.
Question?
Yeah.
I ask. In the formula for green function, what the head of vector harmonics means?
It basically, if I remember correctly, it's just it's something with their indices. Let me find it. It's you can think about this as complex conjugation, but it's not exactly the complex conjugation. Just give me a second. It's basically it's connected with the fact that in order to have like orthogonal expression, orthogonality of, for example, exponents, you need to have something like m minus n phi. So here you need to have I m phi. Here you need to have I minus n phi. And if I remember correctly, the m hat is basically m minus n minus m, or like something like this. But I don't remember it like by heart, but maybe I can find it in maybe I can find it in a fast way. Not here. Not here. Yeah. This head is basically complex conjugation. It's just like complex conjugate. Yeah, so you can express this this green function. It should be a matrix. So in this case, these coefficients, they will not be scalars, but they will be like some other vectors, A, L, M, and the expansion can be written like this: M, L, M plus like B, L, M, N, L, M. Here, it's also important to track the arguments, so it will be like, maybe it will be better to write it like this: MLM of R, dyadic product with some coefficient, some vector coefficient, LM of R prime plus NLM of R, dyadic product with some like LM of coefficient R prime plus LM of R, dyadic product with some another coefficient, of which are like functions of R prime. And basically to get these coefficients, to get this like coefficients, you do the same thing. You
Excuse me, may I have a question?
yeah, of course.
Is it important the order between the multiplication?
No. It's not really important. Well, of course, like let me say some things, because if you have some vectors, I don't know, vector O and vector W, the outer product, or like the dyadic product, is EI, EJ, OI, OW, J. So basically it's a matrix. For example, for vectors for two elements, O1 W1, O1 W2, O2 W1, O2 W2. So you see that O times W is not equal to W times O. Actually, O times W equals to transposed W times U. So in this case, order matters. But here we can write it. We can write this expression like this, like it will be ALM of R prime times MLM of R, and so on and so forth. A prime, let me note it like this, A prime. In the end, if we write it like this or like this, the green function will still be the same. But these coefficients will be different. So this is basically like two similar ways how to derive one thing. The final expression will still be the same. You can derive it, you can write it like this or like this. The final expression will still be the same. So but basically in the end you will just have different coefficients, and of course they are connected with each other because the final expression is the same, something like this. So basically, like, to derive this coefficient, for example, ALM, we can use orthogonality of vector spherical harmonics and write it as, it will be M prime LM M L prime M prime of R multiplied by the green function of R and R prime. Oh, no, like this. Integrated all the whole volume. So we see that because vector spherical harmonics are orthogonal, if we multiply this big expression from the left, here also about like these different orders, in this case you will need to multiply it from the right, and in this case you will need to multiply it like this, like from the left, because yeah, you'll get different things here. Basically such integral will give you this coefficient. It's with dyadics, it's the same as with vectors and with like scalar functions. Basically it's the series, and I don't want like to dive really deep into details. I think we spent like a lot of time for this. But in the end, we have like the following expression. We have the following expression for the dyadic green function, and basically, if we have how to say this? How to say this? If the size of the particle is much less than the wavelength, so how to say this? Just give me a second, please. So basically, we see that we can write this green function in terms of this like vector spherical harmonics, and we remember that this, like, for example, N10 is proportional to the electric field of electric dipole. I don't know, M20, M21 is proportional to the electric field of magnetic quadrupole. It's like quote unquote electrodynamical physical meaning of this vector spherical harmonics. In the case of the dipole, when we have dipole particle, we remember that electric field of the dipole is alpha multiplied by Green function of R is the polarizability of the dipole multiplied by the Green function of R minus of R and R0 multiplied by incident electric field at the position of the particle. This is basically electric field of a dipole, and this is incident electric field. And basically if we will look at the far field limit, the far field limit is K is like model of R minus R0 is much larger than the wavelength. Well, I can't derive it to you right now, but basically we will end with something like this. If you will take this limit, we will have something like this. So this E of R, it will be proportional to it will be proportional to, well, I don't remember the expression, but it will be something like E0 multiplied by, maybe I can find it in the lectures, in the lecture notes. Oh yeah, something like this. So it's like E0 multiplied by 3 divided by 2, A1 electric field, even 1, 0, something like this. Yeah, I don't know actually. Well, I think that to answer, like rigorously answer your question, I need to make a lot of derivations, and we already spent like half an hour on this. So the rigorous expression for the electric field of the dipole is like this. I think like what is important for the lecture is that if we will look at this expression and take the far field limit of this, we will get that polarizability of the particle can be expressed like using this expression. I don't know. Something like this. It just will take us a lot of time to take this limit and derive, like, of course, if you want, I can do this, but I'm not sure that this is really necessary. Why exactly do you want to know the expression like for the electric field of the dipole? Maybe I can answer this question in some like different way. Guys, can you hear me?
Yes.
Like, why exactly do you want to know this like
Can
rigorous
you
expression?
repeat, please?
Huh? Why exactly do you want to know the expression for the electric field of the dipole? What exactly do you want to understand from this expression? Maybe I can try to explain it to you, not with the expression, but with the words.
I wanted to understand only how we get this connection between alpha and A1.
So basically, as I said previously, we can write the scattered electric field. We can write scattered electric field in two ways. We can maybe I can explain this. In the general case, like any scattered field can be written as an integral, as a convolution of the current with the green function. And we know that like from the basic electrostatics, we know about these multiples and all of this stuff. Let me recall how we introduce these multiples, for example, in electrostatics.
I think I can believe you to not spend a lot of time.
Yeah, окей. Так, где я остановился? Так. Yeah, so basically, yeah, we have this expression. We have this expression alpha equals to 3i divided by 2k to the third power a1. We will get this when we will compare the definition of the electric polarizability and our expansion into the vector spherical harmonics. And well, basically, if we will take the series of a1 into x, where x is this is ak here, this is like radius of a sphere. This is here k is omega over c. We will get the following expression: 2, 3 epsilon minus 1 divided epsilon plus 2 x to the third power divided by 1 minus 3 over 5 epsilon minus 2 divided by epsilon plus 2 x squared minus 1 2 over 3 epsilon minus 1 divided by epsilon plus 2. Here it should be 1. X to the third power plus, and so on and so forth. This is basically like this is basically something like power series of this expression for x less than 1, which is like the relay regime. And when we will substitute this expression here, you'll basically get that alpha equals to epsilon minus 1 divided by epsilon plus 2 a to the, maybe let me write it like, it's not like a, but r0 r0 to the third power divided by 1 minus 3 over 5 epsilon minus 1 divided by epsilon plus 2 k to the third power, k to the second power, r0 to the second power, which is just this x, minus I 2 over 3 epsilon minus 1 epsilon plus 2 k to the third power, r0 to the third power. And actually, this guy here is our quasi-static polarizability. This is also called Clausius-Mossotti relation. It gives the expression for the polarizability of the particle as a function of its electric susceptibility in the quasi-static, in the electrostatic regime. Basically, if you will see, we will get that alpha equals to alpha 0 divided by 1 minus this guy here is alpha 0 to the third power, k to the third power. And this guy is like alpha 0 to the second power, k to the second power. So basically we have something like, something else here, and I to the 2 divided by 3, k to the third power, alpha 0 to the third power. And it's very similar to, what we get here. So the main idea that I wanted to tell by everything this is that we can get this, we can get the same, how to say this? So if we will expand our Mie coefficients into the series for small particles, we can get the polarizability of this particle in terms of Mie coefficients, and we can get the same conclusion about like imaginary part of polarizability from this. And like in the end, I wanted to tell you one more thing. We can actually express the Scattering cross-section and extinction cross-section in terms of this Mie coefficients. So we remember that, for example, scattered power can be calculated as an integral of time averaged Poynting vector of the scattered field over some closed surface. So for example, we have our sphere and we close it with some like spherical surface, which we call sigma. And like here, let me write it like this. Here is a normal vector. And this is like the vector normal to the surface. We can calculate scattered power like this. The scattered power is C over 8 pi real part of electric field of the scattered electric field times scattered magnetic field conjugated. So we can write it like this. We can write this expression like C over 8 pi real part of sum from L equals to 1 to infinity AL N electric L and even L0 or it was not 0. It was not, see, it was 1. It was 1. Sorry. Minus it's IAL minus BL magnetic harmonic OL1 vector product with magnetic field, and magnetic field we can write magnetic field as it's like the curl of electric field IK. If you remember, we derived this on one of the previous lectures. So this is this will be minus I. This will be minus I.
Excuse me, could you please scroll a bit higher?
Like this?
Yeah, yes, sir.
Okay. This will be. Oh, I also forgot here. I also forgot here. EL. Basically, we substitute here our expansion for electric and magnetic fields. It will be minus. In the end, we can write it like minus sum over L equals to 1 to infinity EL. Not minus, without minus. Without minus AL M EL1 plus IBL and OL1. This is basically, we get this expression from here. And we have integral of this guy. And in the end, we can write the scattered power as like C over 8 pi integral of the real part. It's L prime everywhere because integral of the real part of the sum L from 1 to infinity, sum for magnetic field L prime from 1 to infinity, EL prime, and here we have something like IAL prime magnetic harmonic EL prime 1 electric harmonic EL1 vector product with magnetic harmonic EL prime 1 and so on and so forth. And when we will calculate these integrals, for example, like we will see that it's possible to introduce one more orthogonality relation for vector spherical harmonics. For example, N EL1 times M EL prime 1 over the closed surface will be proportional to delta function of L prime, and something like N odd L1 times M odd M even L prime 1 over d sigma will also always be equal to 0, because inside of this big integral we have integral of cosine multiplied by sine, which is always equal to 0 over the period, of course. And basically, because of this, like another form of orthogonality relations, we can express scattered power in the end. If you will like rigorously calculate all of these integrals, we will get that the scattered power will have the following expression: sum from L equals to 1 to infinity to L plus 1 square modulus of AL plus square modulus of BL. This is basically, this follows from this big expression. After we calculate all of these integrals, we will get this very nice expression. And if you remember correctly, we can also write, oh no, this is not the scattered power, this is scattering cross-section. We can also, if you remember correctly, remember, we can also express extinction cross-section. It is like proportional to the integral of like C over 8 pi real part of electric field incident times magnetic field scattered plus electric field scattered times magnetic field incident. Here what we do, we express this is basically vector spherical harmonics. We put here the vector spherical harmonics expansion of a plane wave, which we derived, not derived, but which we used for the quote-unquote derivation of the Mie coefficients. If you remember, I wrote this expansion in the beginning, maybe, of the previous lecture. And for these guys, we basically put this expression. So, for example, this expression for the electric field and this expression for magnetic field, we put it like, put it here. Yeah, and once again, we calculate these integrals over the products of vector spherical harmonics, and we can get that the extinction cross-section can be calculated as 2 pi over k0 squared sum from L1 equal to 1 to infinity, but in this case to L plus 1, but in this case it will be only the real part of AL plus BL. So let me like put it, let me put it on one part on a similar page here. So this is expression for the scattering cross-section, and this is expression for the extinction cross-section, AL plus BL. So you see that basically these parts are equal, and for the extinction you have real part of Mie coefficients. For the scattering you have square modulus of Mie coefficients. This is very similar to what we actually get for the dipole particle, that like for the dipole, this is proportional to the imaginary part of alpha, and alpha is proportional to the I Mie coefficient. And this guy is proportional to the square modulus of alpha squared. Yeah, square modulus of alpha for the dipole. So you can see here one very important thing is that energy, for example, if you look at the scattering coefficient, we will see that the scattering coefficient is an additive quantity. That we can take scattering like total as a sum of sigma scattered, the contribution by the dipole with L equal to 1, plus the scattering cross-section of the quadrupole, like L equal to 2n, like so on and so forth. So each of these multiples scatters independently. In other in other words, when we calculate, for example, scattering power, we don't have any terms like m1 multiplied by m2 or like m3 multiplied by m10, something like this. We don't have such terms. We only have terms like m1, n1, like m2, n2, something like this. So it means that all these multiples do not interfere between each other. So there are no interference terms. They're only terms like proportional to products of like each multiples. And we say that in this case, each of these multiples is a scattering channel. Each of the multiples is a scattering channel. So the definition of the scattering channel, it's basically we can use the vector spherical harmonics is only one set of like basis functions. Of course, we can find another set of basis functions, which will be more convenient for other problem. But not any set of basis function will correspond to some scattering channels. When we can express, for example, when we can write electric field as a series of some functions, and when, for example, scattered power can be expressed as a sum, as a following sum, then this means that these functions correspond to some scattering channels. So scattering channels should be orthogonal in the far field, which means they should not interfere in the far field, which also means, like using other words, we can say that expression for the power radiated into the far field or the scattered power should contain only terms like this. There should be like no terms like alpha n prime alpha n. There should be no terms like this. So these scattering channels, they are independent in this sense. And because of this, scattering cross-section corresponds, the total scattering cross-section corresponds to the sum of scattering cross-sections into each independent scattering channel. Something like this. Something like this. So I think that maybe no, I think that this is the end for today. Yeah, it's almost the lecture is finished. So do you have any questions?
About this
Sorry, can you please repeat? I can't hear you. Maybe you can write the question in the Telegram. Because I can't, if you're saying something, I can't hear anything. You can write your question in the Telegram chat and I will try to answer it.
He texted in chat that
Okay.
he doesn't have questions. So
Okay.
Paolo and I
Nice.
haven't questions.
You have a
Thank
question.
you.
Okay.
No,
You have a question or you don't have a question? Sorry.
no, I haven't.
Okay.
Excuse me,
Yeah.
excuse me, our next lectures will be online too.
Yeah, because Daniil is in China
Okay, thank you.
right now. Okay, so guys, thank you very much. I hope it was at least a little bit educational. So thank you very much and see you in some time. Goodbye.
Sorry,
Bye.
can I
Goodbye.
can I ask
Sorry?
about one?
Yeah, you can ask.
Can I speak Russian, please?
Yeah, of course.
Можете, пожалуйста, открыть домашку вот последнюю?
Последнюю домашку открыть.
Да.
Сейчас, давай попробуем. Сейчас я скину ее себе на планшет. Скину себе на комп прям. Так, это мы остановим. Сейчас, одну секундочку. Так, где она у меня? Окей. Так, расшарить экран. Acrobat Reader. Да, видно?
Да, спасибо. Вот в первом уже таске вот я не очень понимаю, ну, в последнем пункте, когда надо разложить плоскую волну по
Да.
никам, я не очень понимаю, в каком смысле надо коэффициенты находить как функции отказа. Ну, в плане там получится просто дельта-функция. И, ну, как бы
Ну вот.
физический смысл этого.
Ну, а смотри, здесь выражение, которое написано, оно написано здесь, так сказать, в общем виде. Вот.
Нет, а в виде разве не должно быть еще разложение, ну, там, по коро?
У тебя коро – это функция k и kz. У тебя, смотри, у тебя коро – это k квадрат минус kz квадрат. Вот, поскольку у нас конкретная k, одно конкретное k, у нас плоская волна при конкретном k. Ну, то есть у тебя, по сути, смотри, у тебя есть как бы, давай по аналогии с декартовыми координатами. У тебя есть kx, ky, kz, у тебя есть частота. Вот. Но при этом, при всем, как бы, казалось бы, 4 как бы независимых переменных. Но при этом, при всем, у нас есть диспрессионное уравнение, которое эти 4 независимых переменных соединяет, превращает в 3 независимых переменных. Ты можешь взять kx, ky, kz и частоту считать через эти 3 переменные. Или, например, ты можешь взять омегу, kx, ky. Вот. И в данном случае, поскольку мы типа все считаем при одной определенной частоте, то есть, конечно, мы можем взять электрическое поле как поле от времени, взять Фурье по времени еще, разложить все это в интеграл Фурье по омегам и так далее и тому подобное. Но чтобы не усложнять себе жизнь, мы сразу же говорим, что у нас вот в этих вот гармониках у нас К, и вот здесь вот К, это типа одно и то же К. И поэтому, когда у нас вот тут вот есть какое-то конкретное К и какое-то конкретное КЗ, у нас коро, оно определено автоматически через К и КЗ. Вот как-то так. И поэтому здесь у нас будет только КЗ. Да, у нас там будет А, например, коэффициент А будет функцией КЗ и коро, но коро при этом будет функцией КЗ. И будет вполне себе точно определяться через КЗ. Вот, поэтому А у нас только функция КЗ. Здесь, ну, поэтому здесь я написал так. Вот.
Нет, ну понятно, ну просто, мне кажется, было бы, ну, как раз логичнее такой геометрии, когда у нас в этом, как там в исходном поле, в принципе, нет kz, то использовать не kz, а karo как раз. Kz уже, пусть будет функция от karo.
Смотри, я здесь исходил просто из той точки зрения, что можно так сделать, можно и коро сделать тоже. Взять коро и через коро определять kz. Вот. Просто смотри, изначально, еще когда ты решаешь скалярное уравнение Гельмгольца, вот здесь вот, я, по крайней мере, привык его решать следующим образом. Я также использую метод Фурье, то есть в плане метод разделения переменных. Вот. Я получаю одно уравнение
Вы имеете в
на...
виду, что там kz раньше возникает просто?
Да, что kz возникает раньше, чем коро.
Ну, окей,
Поэтому,
ну,
типа...
хорошо, если так, ну, там этот коэффициент, BL, например, да, он как бы интеграл e0 умножить на nl со звездочкой делить на интеграл от нормы, от модуля в квадрате nl, да?
Да.
А там при интегрировании по z тогда получится, просто бесконечность, потому что там экспоненты сократятся, так что это вообще тогда значит?
Но оно, типа, смотри, когда ты будешь считать только норму, но это как сказать, ну вот в квантах мы же тоже говорим, что типа а-ля нормируем дельта-функцию. Вот. Когда плоские волны считаем, все вот эти. Типа нормируем дельта-функцию. То есть, понятное дело, что там никаких бесконечностей не возникает. Понятное дело, что поскольку вот эта вот штука конечна, и вот эта вот штука конечна, то коэффициент А тоже будет у тебя конечный. И там типа эти дельта-функции, они в итоге у тебя сократятся, если аккуратно все это более-менее считать. Вот, то есть не писать, что а-ля дельта-функция бесконечность, а просто записать дельта-функцию, там они в итоге как бы сократятся у тебя. Вот.
Не возникает дельта-функции, там просто бесконечность. Типа там будет интеграл от константы по всей прямой.
Там будет дельта-функция от нуля, если строго, типа. Понятное дело, что со всеми вот этими, типа, обобщенными функциями там оно все, там нужно не просто математически все это посчитать, но еще как-то, головой подумать в плане, как делать логично, а как делать нелогично, потому что...
Просто вот мне кажется, что логично вообще по z не интегрировать, а интегрировать только по углу.
Можно и так. То есть тебе же, смотри, тут же тебе же главное просто какую-то ортогональность ввести. То есть можно просто по углу проинтегрировать. Это правда. Но типа вот это вот выражение, еще раз, это типа самый общий вид такого вот. Прям самый-самый-самый общий вид.
Ортогональность будет и при интегрировании по углу, разве нет?
Будет.
Если мы
у тебя, смотри, у тебя при интегрировании по углу будет ортогональность для разных L. Но при этом для разных z у тебя, если я не ошибаюсь, там не будет, кажется, для разных kz у тебя там, кажется, не будет ортогональности. Вот. Но она должна быть. И поэтому нужно еще и по kz тоже интегрировать. Потому что в общем случае, типа, здесь как бы если мы не будем интегрировать по kz, то вот здесь вот этих коэффициентов мы положим, что, допустим, вот это вот m это функция типа kz прайм, мы получим, что эти коэффициенты это функция kz и kz прайм. Вот а-ля типа что-то вот такое вот сложное. То есть я точно сам не помню, если честно, я проделывал это какое-то время назад, но кажется, что интегрирование по kz было нужно, но я могу ошибаться. То есть, я честно признаюсь, я могу ошибаться, но вроде как интегрирование по kz тоже нужно, чтобы как раз-таки вот эти вот экспоненты тоже превратились в дельта-функцию. То есть, сейчас у тебя сверху, смотри, вот если мы вот это вот электрическое поле помножим какую-нибудь типа ml прайм kz прайм.
ML там будет 0, потому что они просто ортогональны.
Да, типа, и мы проинтегрируем это все по kz и по углу. Если мы проинтегрируем это только по углу, то у нас только ортогональность элек получится. У нас там дельта Кроникера получится. Но при этом у нас останется типа и kz, плюс kz prime z. Вот такая вот штука, потому что здесь у тебя будет, вот в этой штуке у тебя будет экспонента и kz, и мы еще умножили на экспоненту и kz prime. И kz штрих, точнее, сори. У тебя будет типа экспонента и kz умножить на экспоненту и kz штрих z. Вот такая вот история. И, соответственно, чтобы от этого избавиться, нам нужно интегрировать еще и по kz. Вот как-то так. Вот. То есть тут проблема в том, как вводить типа норму. Если у нас типа внизу вот этот нормировочный интеграл, да, он там, ну, не совсем хорошо, он там, когда мы интегрируем все это дело по kz, у нас там получается типа а-ля бесконечность. Но эта бесконечность, это на самом деле дельта-функция от нуля. Вот. А здесь у нас вылезет типа тоже там какая-то дельта-функция должна вылезти, кажется. Вот. Поэтому вроде как там все должно быть окей.
То есть как бы это записать как формально дельта от kz делить на дельта от нуля. Правильно
Ну,
понял?
типа того. Типа того.
Хорошо, я понял.
Вот. То есть, ну, давай так. Если вдруг, если я все это еще перепроверю, и если вышло так, что я продолбался, типа такой ответ будет засчитываться. Вот. То, что там типа а-ля у нас бесконечность, но это как бы дельта от нуля. Вот. Но в целом, типа, если я продолбался, скорее всего, это мы что-то придумаем, чтобы вас никак не обижало то, что я продолбался. Вот. Но вроде как все должно быть правильно. Но тут вообще, как бы, тут на самом деле сейчас вот такой вот вид, как бы, вот такой вид плоской волны, я не зря здесь именно из Z взял. Если ты посмотришь и аккуратно подумаешь об этом всем, то тут часть коэффициентов тебе вообще считать не придется. Но по этому поводу ничего особо говорить не буду. Вот. Вот, короче, как-то так.
Спасибо.
Да. Еще вопросы какие-нибудь?
У меня больше нет.
Отлично. Так, ну, если вдруг есть еще вопросы, задавайте. Если нет, то всем спасибо. Goodbye, everyone.
До свидания.